Hello everyone and welcome to this webinar hosted by Oilfield Technology with Swagelok. The title of today's presentation is How to Reduce Leaks and Associated Costs in Upstream Applications, and our speaker is Doug Nordstrom, Senior Product Manager at Swagelok. Now this webinar will cover common problems experienced in offshore medium pressure fluid systems, the difference between fittings technologies used in these applications, what affects total life cycle cost of fittings and why it matters, as well as strategies for countering vibration, corrosion, and other threats to fittings. Following the presentation, there will be an opportunity to put your questions to Swagelok in a live Q&A session. So we'd like to invite you to submit your questions throughout the course of today's presentation. So for those of you that are joining us on a mobile or cell phone, you can access the question box by simply tapping the icon at the bottom of your screen. And for those of you that are using a desktop or a laptop, just click on the orange arrow on the right-hand side of your screen to open up the user interface, and then you can go ahead and type your questions into the box. Now, before we get started, I also want to let you know that everyone who is registered to attend this webinar will be emailed a full recording after today's session. So, without further ado, I'll now hand you over to Doug for his presentation.
Thank you, Callum, and thank you everyone for joining. Let's see if I can get this to go forward. Yep, and like Callum mentioned, I am a senior product manager at Swagelok. I handle the FK fittings, excuse me, and the hose products at Swagelok. I've had other experience at Swagelok where I've managed the valves and regulator product lines, done some new product development efforts, and worked in the chem and refining market as a market manager for some time. I've been at Swagelok for 28 years, started right out of school, where I went to school at Case Western for a mechanical engineering degree. So with that, let's get into the presentation. We're going to start with discussing what it takes to create a seal, right? Every fitting is there to make a seal between two components, usually tubing and some valve or some other product. And we want to understand what that is versus permeation. When we then look at different fitting designs, fitting technologies, we want to make sure that we can evaluate how that fitting technology can protect the users from permeation, from leakage, from burst, and then other failure mechanisms like Callum mentioned, which is vibration and corrosion. And then we'll go through a little bit of a history on different fitting technologies and how they can compare in those different factors. And then we have an example at the end, briefly going through what the Swagelok FK fitting is and how it is designed to withstand those different failure modes. So with that, let's get into what creating a seal is versus permeation. So when we create a seal, which is what the gray piece is intended to be in those pictures below, it's basically there to stop molecules, gas or liquid, on one side to reaching the other side. That's what a seal is. When these molecules reach the other side, we consider that a leak. There's two types of leaks, and what we're saying here is that the two types are a path leak or permeation. What a path leak is that's typically what we think of as a leak. It's a continuous pore structure. In other words, it's a continuous gap in the seal between the two components that is intended to make a seal between. So what I'm showing in the path leak picture is two types of path leaks. One is where the seal is not pressed against the sealing, the mating surface well enough, so there's a gap, and those molecules are flowing through that gap to the other side. The other is when the actual seal itself is cracked, and so there is a gap or a continuous pore structure from one side to the other, and molecules flow through the seal. These can be solved through different sealing forces, and we'll talk about that a bit. Permeation is actually, there's no gap, there's no continuous pore structure, but the seal material is too absorbent. It absorbs the molecules. Many times in this case it's a gas, and those gas molecules flow from one side to the other just through the material itself. The way I describe this is it's like a plate of spaghetti where you put spaghetti sauce on top of the spaghetti, and eventually it'll get down to the plate. It doesn't look like there's a gap, but it flows right through the material to the other side. Now, different things that can drive permeation rates to create higher and higher leakages through permeation are pressure, temperature, and seal length. Now, pressure is perfectly linear with permeation. So if you double the pressure within a particular fluid system, it will double the permeation rate through the seal material. So for example, a 10,000 PSI system will permeate twice as fast as a 5,000 PSI system. Temperature is also linear, completely linear, but it's linear with a relationship to absolute temperature. So, a 4,000 or 400, I'm sorry, Kelvin gas, which is 127 C or 260 Fahrenheit, is going to permeate only 33% faster than a 300 Kelvin gas, which is more like room temperature. As these gas molecules heat up, they become faster, they have more energy, and they'll permeate faster, but it's again relative to absolute zero. And then lastly, the seal length. And this is where we start getting into fitting design technologies. Different fitting designs have different seal lengths, the way they are mating with the tubing or the other surface. And so it's always good to evaluate what the seal length is of a fitting technology. And the longer the seal length, it lessens permeation rate by a square root function. So it's not as helpful as, for example, lowering the pressure, something that's a linear function. So when we look at different fitting technologies, which we will here in a bit, we want to look at what the seal length is within that fitting technology. But then lastly, of course, it's the seal material, which has to do with the sealing technology, but also what gas is being used. And when we look at what those are, we see some vast differences in performance. So given everything else being equal, if we say a nylon seal in nitrogen gas gets a permeation rate of 1, whatever that unit is, 1 liter per hour, or 1 milliliter per hour. But we set everything else equal so that that's a 1. You can see how the gas molecule and the seal material can have vast differences in performance. And they're not always, it's not always logical the way they change. You can see as we use nitrogen with different seal materials, Buna and PTFE, which is Teflon, perform the same. With oxygen, they don't perform the same. And you can see Viton is actually the worst with nitrogen, and it's not as bad with oxygen. It's still 2,900 times as much as nylon with nitrogen, but they change, and that's because of the seal material makeup, how the pore structures within the seal material are formed, and the actual gas molecule is shaped. They're going to flow through the different materials at different rates. And you can see also as I go left to right, the gas molecules are getting smaller. As they get smaller, of course, they're going to permeate through the material much, much faster, where hydrogen with a Viton seal is going to permeate 45,000 times as fast as a nitrogen molecule will permeate through an equivalent nylon seal. So when we look at fitting technology, we want to make sure that we understand that even though the fitting may be made up correctly, it still could be quote unquote leaking due to permeation based on what the material is making the seal and what the gas is within the fluid system. So throughout this presentation, I have these factors to consider when looking at a fitting technology. So the first one we want to discuss is what is the likelihood of permeation? How long of a permeation path does that fitting technology have? And is it going to create a permeation leak through the fitting? So when we look at then creating a seal versus permeation, really creating a seal means we have two mating surfaces and we're pressing them together. We're trying to press them together so that it eliminates the continuous pore structure. Typically, these components are machine surfaces. These machine surfaces have a certain roughness to them, and that's what I'm trying to show in these crudely drawn gray pieces. These machine surfaces are being pushed together harder and harder. I start with the low force on the left side and go to a high force on the right side. And again, what we're trying to do here is eliminate that continuous pore structure. So on the left, these pieces are barely touching, very low force. The advantage of this is there's very low deformation or no deformation really, and it makes these pieces last, these sealing surfaces last a long time because there's no real force that's deforming them. As a result, though, there is very poor sealability. It may require some lube or something to fill that continuous pore structure to stop any kind of leak. This could be a nice way to seal if you just have an air line or water line or something where you don't really care about leakage. But again, it's going to have very poor sealability. As we move to the medium force, this is where the deformation really is on the elastic scale, so it can move back to where it previously was. These pieces still last a long time. This is really what, when we design valves, they're going to see high cycles. We use this type of sealing, this medium force, because the valve is going to need to seal time and time again. It's not going to be quite as strong as what we call the high force. So this is where these components are being plastically deformed into each other. A lot of times this is through a burnishing type process where they're really rubbing into each other and creating a very, very tight seal. And these pieces, though, won't last a lot of cycles. They can't be made and remade thousands of times, but it will be a very, very tight seal, which is ideal for fittings. Fittings typically don't go through hundreds or thousands of remakes. They go through a dozen remakes or so. So what we're looking for in a fitting technology is something that's going to drive high force so we can get a very, very tight and reliable seal. So with that, we want to get into some other fitting design factors and whether or not they make a nice, tight, reliable seal. So the first thing we do when we look at a fitting design is determine what the leak path potentially could be. And there's an equation that is used to determine what that leak could be, and we're not going to get into too many details with it, but the factors included in that equation are the differential pressure between the inside and the outside of the fitting. The height is a cubed function, and what that height is, I'm trying to show in those pictures, is the potential distance between the mating surfaces, and it's a little easier to see maybe on the bottom picture where I have my crudely drawn pieces. The more and more sealing force, the less and less that height becomes. So that's why we're looking for a very, very strong sealing force so we can minimize the height, because again, it's also a cube function. The width is basically the distance around the seal. It's the diameter, which usually has to do with the size of the line that we're trying to put the fitting on. And then there's also the viscosity and the length of the seal. So we want to increase the length as well. So I'm showing that in the bottom picture. Also, the longer the length of the seal, the less of a leak path we'll have within that, because there's more chances for that seal to occur. So a good fitting technology, again, is going to have minimal height, so stronger seal force, and it's going to have a longer seal length. So when you look at different fitting technologies, you want to keep those in mind. Now, when we look at how a fitting fails with overpressurization, we always want the tubing to be the weak point of the system. For this presentation, we're going to assume that's the case. That really is more up to the fitting manufacturer, not the fitting technology. So we're going to assume that the fittings are all rated to withstand the burst pressure of the tubing that it's being attached to. But it is important to take that into account when you're choosing a particular fitting. Ask the fitting manufacturer, is it rated to the burst pressure of the tubing? The answer should always be yes. But you want to see the types of failures I'm showing in these pictures where the tubing itself fails. A fitting blowout can be very dangerous because the tubing can essentially whip around and cause serious safety concerns. So we're going to assume that's the case. But when creating a fitting makeup, when connecting a fitting, we want to determine if the fitting is made up properly, because a fitting rated to the tubing pressure, if improperly made, if improperly connected, can still fail at the fitting. And so we want to determine if that fitting technology is able to be determined if it's properly made up. because that way it's a safer environment. Of course, you can check to see if these fittings were properly made. So the factor we're looking at here is it possible or is it easy to determine or identify if the assembly was properly done? And also how easy is it to properly make up that fitting? Next is vibration fatigue. Fittings many times see a lot of vibration, and the design or the technology of the fitting can withstand that vibration, some better than others. And the obvious example here is this paper clip, where if I take a paper clip and bend it back and bend it and bend it back, we all know that eventually that paper clip is going to fail. But what determines how long that paper clip lasts until it fails? Things like bending distance, bending speed, and that's essentially the vibration amount, right? How much it's vibrating, how far it's vibrating. But then there's some things within that motion that I can control with fitting technology, and that's how well is that supported. If I support that with my fingers much better as I bend it back and forth, the paperclip will last longer, even though I'm bending it the same amount. And that's where we come into fitting technology and fitting designs, is how well is that supported within the fitting. And then of course, material properties, which many times is driven by what's needed for the particular application, is going to depend on how well the fitting lasts in vibration. So there's some industry standard things that or tests that people do. Many fitting manufacturers do this, where we make up a tubing system using whatever fitting we're testing, and the other side of the tubing is moved up and down to represent the vibration. So that's essentially the bending speed and bending distance. But what we're testing here is how well that fitting is supporting the tubing on the stationary side. We measure how long this lasts, and different fitting technologies last different lengths of bends, different amounts of bends. So when looking again at what we want to use for a particular system, we want to say, how well is that tubing supported within the fitting so that it'll withstand the most vibration before it fails. And then lastly, it's the amount of corrosion that fitting can see. Now, sometimes this is not a concern because the media or the environment the fitting is in is not corrosive at all, so it's not really a problem. But many times it can be a problem, either because of the media flowing through the fitting or the environment the fitting is in, such as seawater or salt spray or something. And there's different variables here that can determine how long that fitting is going to last. Like the obvious one is the material the fitting is made of. And there's things we can do. There's exotic alloys and things that will last a long time, but there's also ways to control the way stainless steel is made and the compositions within the stainless steel to have it last longer. You know, the example I show here is the one I'm familiar with, which is Swagelok stainless steel, where we control our chromium and nickel at different amounts than a lot of industry standards to allow the fitting to last longer. A lot of fitting manufacturers do the same kind of thing. But the fitting design itself can determine how well the product lasts in a corrosive environment. And what we look for is can the media or the environment, whatever the corrosive situation is, can it stay stagnant on the fitting? And the more stagnant that corrosive media can stay, the more it will corrode, the quicker it will corrode onto the fitting or corrode the fitting. So we want to look at entrapment areas, outside or inside. Can salt spray sit on the outside of the fitting very easily, or are there entrapment areas on the inside of the fitting where corrosive media can create fatigue? Okay, so when we look at these different fittings, which we're about to do, we want to say, you know, is there a permeation path? Is there permeation material? Is there a permeation path through the fitting? And how much of that permeation path is, how long it is? How much force does the fitting put on the sealing area, right? We want to minimize the H, minimize the height. How long is the sealing area? We want to maximize the L. How easy is it to determine if the fitting is not properly made up? How well is the fitting support tubing? That's usually what we're sealing the fitting onto, right? How well does it support the tubing for vibration? And does it have entrapment areas that will create corrosion? So with that, let's take a look at some fitting technologies. And again, this is intended to be a bit chronological. So we're going to start with really the original fitting for these fluid systems, and that's a tapered thread, a pipe thread, otherwise known as, right? So the way this technology works is there's a slight taper on the male and the female end. The male end is usually wrapped in a Teflon tape, as seen in that picture, and then threaded in until really it can't be torqued anymore. It's torqued in to the point where you feel a seal has been made. This torque can be extremely high, so there's a lot of force, right, which is nice. That's what we're looking for, minimizing the H. The problem with this, though, is Teflon is a permeation material. So there is a permeation path, which I'm showing in red. It's a very long path, so that's good, but the Teflon will permeate, so gases will flow through the Teflon tape and eventually get to the outside. Again, it's a long path, but it will reach the outside. This is not well supported really with vibration, but because the Teflon tape seals throughout that entire length, there is no real dead space that will create a corrosion entrapment area. Because the amount of torque or the amount of turns it takes to create this seal, there's no way to tell what was torqued or how much it was torqued. So you don't know if the fitting was made up properly. There's no identification method to say that one has been torqued enough or this one has not been torqued enough. So there's no way to say, is this fitting been made up properly? So when we look at the way that fitting technology ranks against what we're looking for, it does have a permeation path, but it's very long. So I'm saying that's yellow, that's in the middle. It has a lot of sealing force, has a lot of sealing area. So it's a nice, reliable seal for the most point. It doesn't have a way to determine if the seal was made up properly. It doesn't have very good flex support, but there's no entrapment area. So that we're giving this a rating from orange to green as far as how well that fitting technology works. So because it didn't have a way to identify if the fitting was made up properly, people started looking at ways to design fittings so that they could be gaugeable or they could be identified. And the first thing that was invented was an O-ring seal fitting where there's a male and the female thread, straight thread, and there's an O-ring either on the ID, which you see on the left, or on the neck, or the OD, which you see on the right. And these nuts are threaded together until they bottom out, and you can tell if it was made up properly. So that was the big advantage. The downside is, though, of course, O-rings are going to permeate very quickly, like we showed, and there's not a lot of area on the O-ring, so it's a small permeation amount, permeation distance. So these are going to permeate much more quickly than the tapered thread we looked at. The O-ring material itself also is going to have to be compatible with the system media. And in the case of the neck O-ring, the one on the right, there's a lot of entrapment area on the inside of that fitting. So there can be some stagnant corrosion going on where the fitting wears out from corrosion very quickly. So when we look at this one, really what they improved upon here is that assembly ID. So that went from the orange to a green, but this design really had some downfalls, some negatives in other areas like sealing force, permeation distance, sealing area. It still doesn't help with the flex support. So it's not the most ideal design. So people said, let's get rid of the O-ring. And we designed this flare style fitting where there's two metal pieces coming together in an angle. And that angle is intended to drive the force into those mating surfaces, creating a burnishing effect, but still maintaining the gaugeability of the fitting design. So it still maintains gaugeability, but eliminates the possibility for permeation. The The downfall of this one, though, is it's a very small sealing area. And as those sealing surfaces come together, they're not well supported. Any kind of vibration on those metal surfaces are going to crack the sealing area and create leakage, and eventually will just wear the fitting out. It does not last long in vibration. Another way to do this, it's essentially the same type of design, but we call them a diesel style fitting. I've also heard these also referred to as flare style fittings, but there's a machined surface that is the body, which I'm showing on the left, and the tubing is actually manipulated into the shape that you see on the right. This is done through special equipment, which is required to make these, to force the tubing, bend the tubing, smash the tubing into the cone shape you see on the right. So that's required, requires specialized equipment to do that, but it has the same basic design features as the flare style I just showed. So there's a nut on that manipulated tube end that threads into the body, and it acts very similar to the flare style. As these pieces come together, it was intended to be quote unquote blowout proof, because the tubing itself now is larger than the neck of the nut that it's going onto. So unless the threads shear that it's put onto, it's quote unquote blowout proof. But again, it's very similar to the flare style as far as the way the fitting performs. Very small sealing area, very poor performance in vibration, but the sealing force comes together and creates that burnishing. So if it's in the right environment, it can create a very reliable seal. So people want to improve upon that, and this is a very popular high pressure fitting technology, which is called cone and thread. This is still used today quite a bit. And what we're doing here is we're creating that same flare style sealing surface, but by doing so, we're actually taking the tubing and machining a cone onto the end of the tubing, and then also behind the cone, we're machining a thread. So again, requires specialized equipment to make that sealing technology, but we're creating a very similar flare style. The design you see on the left is usually used up to 15 or 20,000 PSI. On the right, it's used up to about 60,000 PSI. Very similar in design. There's a collar that is threaded onto the tubing thread, and the nut or the gland is then threaded into the body, and the collar is intended to act as a blowout proof design. Now the issue here is, as those cone and the thread are machined into the tubing, that's a very manual operation many times, and if the threads aren't machined into the tubing properly, those threads can shear fairly easily. So although it's intended to be blowout proof, it has been known to actually blow out. So it's very important that those are done properly, and they're again done usually out in the field. To determine if these are leaking, there is a weep hole usually in the fitting body. Now that weep hole is great for measuring if there's a leak, determining if there's a leak, but it does act as a stagnant area in corrosive environments. So many times these are used near the ocean for offshore rigs and things, and so any salt spray that gets in there can start to corrode right at the sealing area. So that's something to be concerned about here as well. So again, the thread and cone are usually put onto that tube in the field, which is not always the easiest thing to do. It does offer a blowout proof, and it's an identifiable sealing area because of the tolerances of the machined pieces. It does still have that low sealing area though, and it also doesn't support tubing very well, so it is not very high performing in vibration. Many times there's grease used to create these seals as well, which is never really ideal because that grease will eventually evaporate away or go away, wash away, and what's left is a leak path. So we don't always want to rely on greases to create your seal. So when you look at those next three, they really perform, they act very similar to each other. They got rid of that permeation. That was why they were designed, and they're offering this angled sealing area that the flare started, and they all use that type of cone. The cone and thread really ramps up the sealing force, which is great for minimizing that height, the H distance, but they all still fail very regularly in flex support. So vibration still is the downfall of a lot of these sealing technologies. So to combat that, companies started designing what we call a ferrule style design. And this ferrule style design is intended to give more support to the tubing throughout the sealing area and improve that vibration performance. So this ferrule essentially is acting as an O-ring. It's a sacrificial ferrule that is smashed into the body, very similar to the flare style body, and it bites into the tubing, creating some burnishing and a very high sealing force. And again, it supports the tubing much better than the previous designs, so that it will perform better in vibration. Also, it maintains the gaugeable factor because the ferrule, nut, and body are all machined to tolerances that can be used to measure the gap between the nut and the body. So a lot of advantages here that this one brought, but really what it's trying to do is improve that flex support, which it did. A single ferrule design will improve the way the fitting performs in vibration. It also, eliminated permeation, has a high sealing force, still fairly low sealing area though, because it's just right where the ferrule is around the tubing. So that length, the L distance, is relatively low. So the final real fitting technology we want to talk about is what we call two ferrule style. I think everyone probably is aware that Swagelok offers this one. We offer a lot of the previous ones as well. But this two ferrule style is intended to continue to improve upon that tubing support for vibration performance, but also increase the sealing area to make that L distance as long as it can be. So what we have here is a two ferrule squeeze onto the tubing, and basically the back ferrule is what we call colleting onto the tubing, or at the hinge point, I guess you could call it. And the front ferrule is being driven with extreme force into the wedge of the body and into the tubing, which creates a burnishing effect. Again, this one, as probably people are aware, is very easy to be gaugeable. You can measure the distance between the nut and the body shoulder to determine if it's been made up properly. And it has very, very long sealing area, very, very long L. The only one that actually beats it is the original one we talked about, the tapered thread that has the entire distance of that tapered thread as the sealing area. So this is generally considered the best performing. Of course, each one of these, one thing that's key to remember is each one of these comes at a different price point, of course. There's more complexity usually as we go from left to right. So that usually comes with a different price point. So this chart is intended to basically show that you essentially get what you pay for. So when we get to the two ferrule design, again, it has no permeation, has very, very high sealing force. The sealing area, again, is second only to the tapered thread design that we talked about at the beginning. It's gaugeable, very good flex support and vibration, and no real stagnant area similar to the single ferrule. So we want to discuss how we at Swagelok applied this to what we call our FK series fitting, this knowledge on how ferrule designs work. So this is a picture here of the nut and the ferrules of an FK fitting. It's on a red arbor. It's just an assembly holder piece, and this is put into a body with a female thread, of course. This fitting was designed to give us all the advantages, essentially, of the two ferrule technology and reach 20,000 PSI as a pressure rating. It does all of the things we just mentioned about with burnishing to create nice gas seal. It has excellent tubing support, very, very long sealing length, very high performance and vibration. Now, when we also put this technology into our fitting, we make up these fittings by one full turn into the body, but we also can make these fittings up by a torque rating, which is a nice feature if you would rather do it by torque instead of measuring the amount of turns. It's a gaugeable fitting, so we can tell if it's made up properly. And then again, that arbor is used to hold the ferrules and the body all together so that there's no need to worry about misassembly due to ferrules being backwards or missing. The ferrules, because this is being squeezed together, the sealing force is so high in these cases that we need to withstand 20,000 psi. We need to go through a hardening technology, a hardening process for the ferrules, because they'll get smashed too early during the assembly process. So these go through a hardening process that we call SAT12. It creates a tool steel, basically, hardness in the ferrules, and it allows us to increase that burnishing effect to make the seal force higher and the sealability much more improved. This is what the picture looks like when made up. So you can see the two ferrules, the front ferrule and the back ferrule, the male nut, which is threaded into the female body. And as that nut reaches full assembly, the bottom, or I should say the front, I guess, of the nut hits the bottom of the female body, which I'm showing in the blue circle there. And that feature there makes this product assembled by torque. So we can either fully turn it one time after finger tight, and that creates the seal, or we can torque it to a certain rating. And when that torque hits, or when the body hits the bottom of the nut, the torque spikes, and that reaches our torque rating, ensuring that the seal is properly made. What I'm showing with the little diamond piece, triangle piece in the bottom, is the gaugeable feature, where that gauge can be put into the neck between the nut and the body. And if it goes in, that means it wasn't fully assembled. It's a no-go gauge. So if it does not go, that means it was assembled properly. So we can ensure that this is going to be a properly made up seal. So to summarize basically what we went through, we want to make sure that we are evaluating the fitting technology for an application, making sure we're picking the right one for whatever you're putting this fitting technology into. The things to consider, of course, are how much vibration is this fitting going to see? How well does the fitting technology withstand vibration? How important is this safety to the application? Is it simply an air line or a water line where some permeation can be accepted, or is this something that is high pressure and corrosive gas and safety concern? How important is permeation, to eliminate permeation, I should say, right? Is an O-ring going to cause permeation and a safety concern to people around that fitting, or is permeation not really a concern? Always keep that in mind when determining what fitting technology to use. And then lastly, how much corrosion is this fitting going to see? Is it in a corrosive environment? Is the media itself corrosive? And how much, does that fitting technology have stagnant areas of corrosive gas or corrosive environment that are going to wear the fitting away? Even the important thing to keep in mind here is even the highest quality fitting from the best quality, companies, but put into the wrong application are going to have poor outcome, right? It's a poor selection of fitting technology. So we see that quite a bit, where someone's trying to use a fitting in a particular application, but it's just not the right design fitting for that application, and so it's not going to last as long as it should. And as we move along that spectrum that we just went through, we're getting higher and higher priced usually. But as you go to those higher prices, a lot of times that fitting will last longer and make it actually a lower cost of ownership, we call it, because it's lasting longer than a lower price technology. Okay, and with that, I think we want to take some questions. I appreciate everyone's time this morning.
Okay, Doug, thank you very much for that really interesting presentation. As you mentioned, we're now going to move on to the Q&A session. I can see that we've had a few questions come in already, which is great. If you do have a question for Doug and the team at SwageLog, there's still time to send it in to us. Now's your chance. I'd like to encourage you to submit your questions. As a quick reminder, if you are using a mobile or a cell phone, you can access the question box by tapping the icon at the bottom of your screen. And for those of you that are joining us on a desktop or a laptop, just click on the orange arrow on the right-hand side of your screen, and this will open up a user interface, and you can go ahead and type your question into the box, and we'll try to get through as many as we can in the time that's left to us today. So, Doug, first up today, I noticed in your summary box of factors to consider that the tapered thread design had a nice green dot next to the corrosion or compatibility column, signifying that it is the best performing. But can you tell us a little bit about how a tapered thread design can protect against corrosion specifically?
Yeah, so that's an interesting question. So there's some assumptions with that type of sealing technology, that tapered design. If you remember, there was a Teflon tape that is put onto that seal, to that thread. And the assumption with that corrosion green dot is that that tape is properly put onto the thread, and so it's down to the bottom and up to the neck. So that seal is made that entire length. So there's no place for any corrosive material to get inside of that sealing distance and remain stagnant. Now, if that thread isn't properly, if that tape is not properly installed, or it's not the entire length of that thread, it can be a poor performer. So it's important that that tape is put on the length of the entire thread in order for it to maintain the corrosive performance.
Okay, great. Thanks, Doug. And when talking about the Conan thread, you mentioned that the use of grease isn't ideal. So can you just tell us a little bit more about why the use of grease is a concern when creating a seal within a fitting?
Sure, a very popular way to create a nice seal is to put grease on it. A lot of valve manufacturers do that, and it's a good way to clog up that the continuous pore structure. The problem with doing that, though, especially with a fitting, is that grease will continually wear away. It'll either evaporate away in some cases, or it'll wash away. And what's left when that washes away is now a continuous pore structure. So if you're relying on that grease to clog up that continuous pore structure, it will, but it will temporarily, and it might take a year to wash away, but or 2 years or 3 years or a month, but eventually it will be gone and there will be leakage.
Right, great. Thanks, Doug. Can you also describe again what makes a fitting gaugeable and why that is so important?
Sure. So the original fitting design, the pipe fitting, the threaded taper design, there was no way to tell if that was torqued into the body the full distance, because each one was made differently, and it was different amount of turns to create the correct amount of torque. Um, the problem there was that fittings could be loose and that people didn't know if it was completely tightened, and you create some blowouts. So they wanted to make a way to measure if the fitting was torqued properly or tightened properly, turned properly, whatever it might be. And the way they do that is through the distance between a nut and the sealing body. So with SwageLock fittings or other fitting companies, they have a way to measure that distance. And sometimes the nut butts right up against the body, so there's no gap, and they then know that it was torqued properly. But there's a lot of times a distance that can be measured to say, was that fitting tightened fully? And if it meets a certain distance, or it's less than that certain distance, it must have been tightened fully. This way, someone can go around and do a check to see if their system is safe to now pressurize.
Great, thank you, Doug. So we've got time for maybe one or two more questions. So if you've got a question for Doug, this is your last chance to send it in to us. So please get it over to us and we'll see if we can get through it. A question that's come in is asking what type of online sealing material you would suggest for a valve gland packing leakage, where the hydrogen leak is at 650 degrees Fahrenheit and 350 PSIG.
Oh wow, that's specific. Yeah, so for a valve, so for hydrogen, first of all, is going to be a very difficult. It's a very difficult media because of the small molecular size, and so for a seat on a valve, we usually recommend metal in that case. But for, I think the question you said was a packing. So for like a stem packing or something for hydrogen, we would want to look at using as dense of a fluoropolymer as we can. A lot of times hydrogen is best with nylon, I believe, if I remember correctly. And you would want to use a very large packing design. So when looking at a valve handle packing, you would want to see how large that packing is. You would want to have it be as large as possible. I think I would recommend nylon, but we might need to do a little research there and we can get back to that person.
Great, thank you, Doug. Another question that's coming in is asking, are there any computer programs that we can use to check if the tubing lines or fittings can withstand certain amounts of vibration or stresses?
So we do some computational fluid, not computational fluid, we do some finite element analysis with our vibration. The problem with using that is we usually need to get some baseline test data first, right? Because it's very difficult to say this is how long that technology is going to last in a particular vibration without having that baseline data. So what we do is we have a lot of vibration testing equipment, and we do that baseline testing, and then we can manipulate the design with our FEA software to see if it improved or got worse. But that initial testing is always needed to get us on the right path.
Great, that's really interesting, Doug. I think that we're coming towards the end now. But before we do wrap up, Doug, was there any closing thoughts or comments that you had for our viewers today?
Just to keep in mind, that those fitting features when looking at what fitting is best for your system, and not always, the cheapest or most readily available is the best, just because it could create some danger points. So I hope it helps people evaluate fitting technology, and you can determine what you're looking for based on your application.
Great, thank you, Doug. Unfortunately, that is all we have time for today. If you do have any more questions for the team at SwageLock, or you'd like more information, you can head over to swagelock.com, where you can explore some of the solutions that SwageLock have available. Please also keep an eye on your inbox for an email from Oilfield Technology, where you can request more information about reducing leaks in your upstream applications. And we'll also be sending over a recording of today's presentation shortly, so that you can go back over anything that we have discussed today. So thank you again to Doug, and thanks to everyone for joining us.
Yeah, thank you.